All right, friends, it's home stretch time. We leave parametric curves sort of behind and spend our last few lessons taking a look at polar coordinates, polar curves. And the whole thing is birthed from an idea that's just a little bit weird. Just a little bit weird. If you're in the third grade and a teacher puts that point on a coordinate grid and asks you, where is the point? Well, how do you give coordinates for that point? Well, you count some distance over, call that distance x, and some distance up, call that distance y, from some fixed point of reference called the origin, and we call the coordinates of that point x, y. Except that that choice is completely arbitrary. You could just as easily say that this point is determined by a distance from the origin, call that distance r, for reasons that should be fairly obvious. And then you might be thinking, well, there's lots of points that are r away from the origin. Let's have some theta with respect to the horizontal axis. Let's have some theta. And once I give you a distance from the origin and an angle of rotation, I have one and only one point. Coordinates like these are called rectangular coordinates. Coordinates like these are called polar coordinates. Polar coordinates because really there's only one axis and it's this one, and this one is called the pole. And so then to get a point, you go some distance from the origin and you spin around the pole. And how far you spin around the pole determines where the point ends up. Now, on the upside, if I give you a distance from the origin and an angle of rotation, that determines one specific point. But there are many different ways to say this, and I'll show you what I mean. Let's not confuse the matter. I'll show you what I mean. This is what graph paper looks like when you're in polar mode. So you've got your origin here, and let's pretend that I want to find the point 2 pi over 4. So I come out from the origin a distance of 2, and I rotate, yodelay, yodelay. This right here is 2 pi over 4. However, you could also get to this point by going 2 out from the origin and rotating 9 pi over 4. Or you could get this point by going 2 from the origin and rotating negative 7 pi over 4. In fact, there's lots of different ways. You could start at negative 2 and rotate by 5 pi over 4. I can start at negative 2 and yodelay, 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 there it is. There's a whole bunch of polar coordinates that could represent this point. And that's part of what makes polar coordinates just a little bit weird. The other thing that makes polar coordinates just a little bit weird is that we have no experience with such a grid. We're so tuned into XY, we have no idea what to do when people ask you to graph things like r equals 2. If you're graphing r equals 2, you're looking to graph all the points that are a distance of 2 from the origin, and that seems to be fairly straightforward, n'est-ce pas? And graphing theta equals pi over 4, well, that seems to be fairly straightforward. Here's a line on an angle of pi over 4 with the pole, with the positive end of the pole. These points are fine also because if I take -2, 0 and rotate pi over 4, I end up on the blue line. So I don't just get a ray, I get the whole line. Okay? So time for us to do everybody's favorite thing, convert! And we convert both ways. We convert from rectangular to polar, and we convert from polar to rectangular. And you have to be comfortable going both ways. You've got to go both ways. If I give you x, y, you have to give me r theta. And if I give you r theta, you have to give me x, y. And the key each time comes from this picture from 2 slides ago. Right? So if I know x and y, I mean, I can measure over and up, how do you get r? Well, r comes from the Pythagorean relationship. So I can find r, that's not a problem. How do you get this theta if all you know are the blue lengths? Well, that's opposite over adjacent. Tan of theta is going to tell you what theta is. You're going to use tan to figure out what theta is. Now, small warning here. Warning, warning, warning. I did not write that theta is the inverse tan of y over x because that's not always true. Not if theta is in the second quadrant or the third quadrant. So this will help us to find theta, but context will tell us what quadrant we're in. What if we know an r and a theta? How do we get x and y? Well, how do you get x? Well, what's the relationship among these three things? The cosine of theta is x over r, so x is r times the cosine of theta. And similarly, y is r times the sine of theta. So if I give you a distance from the origin and an angle of rotation, you have really quick ways to come up with x and y coordinates. And you have to be able to do that. So, for you to consider, and these are some awesome OYOs, I would like you to graph some things. This is a polar equation. I want to know what that looks like. That's a polar equation. I want to know what that looks like. That's a polar equation. I want to know what that looks like. And that's a polar equation. I want to know what that looks like. So some of this is going to be guided by algebra using these bits of information to convert from polar to rectangular here. You may also choose to use your calculator because, oh, permit me for a moment to completely uncheck this. We were talking about how calculators have different modes, and on your calculator, func is the one that's normally highlighted. Parametric is the one we've been working in for the last week. But if you ask for polar, oh, that's a fun thing now, isn't it? You can graph things. So what if I choose to graph r is 3 times cosine theta, and I gotta do some work to get a theta. What if I graph that? I can get a graph of what r equals 3 cosine theta looks like. And then when I do the algebra to confirm that, I can get a sense of why it looks the way it looks. Just something to think about, something you might want to think about. You can use your calculator to get a sense, a rough idea of what these curves should look like. So that's my encouragement to you. Take some time, figure out how to graph those suckers on your TI whatever, and then see if there's a good algebraic way to justify why the graphs look the way they do. So I'm going to stop deliberately early because you're going to need some time to play. All right, see you in class.